Hello and welcome to SETI Live. I'm your host Beth Johnson, communications specialist here at the SETI Institute, and it's been a week. Welcome to our viewers from around the world. Thank you for joining us. Please let us know where you're watching from in the comments, and also welcome to our listeners on the podcast version of SETI Live, available on most podcast platforms. Today, I have the privilege of welcoming Dr. Janice Bishop, a senior research scientist and the chair of our planetary exploration group here at the SETI Institute. Janice has been doing research on Mars for probably longer than she would like me to admit to, and recently published a paper talking about why Mars is red. So we're here to talk about that and what it means for Mars research, what it means for life on Mars, and all of those sorts of things, and also a little bit about Janice's musical talent. So we'll get to that a little bit later. If you're joining us, please, once again, put in the comments where you're welcoming us in from. And thank you, Janice, for being here today.
Hi, Beth. I'm excited to join you, and I love talking about Mars. So it's great to be here today.
So Janice, is Mars rusty? Is that why Mars is red?
I guess I would say Mars is oxidized and has some characteristics of rust, but it's not rusty like a rusty nail. And I don't think we have to worry about something falling apart like you do with rusty things. But definitely Mars has iron oxide bonds like we see in rust, and the ferric nature of the iron, so the iron 3, the oxidized form. But the surface of Mars is covered with a bunch of minerals that tell us about the ancient history, and ferrihydrite is one of those minerals. And I've been studying this a long time, like you said, but there's a recent paper led by a colleague of mine that's helped us nail down really that the ferrihydrite is the mineral causing the color rather than hematite or some other iron oxides.
And that's really the key here, is that there was the debate as to what mineral was causing the redness, the oxygenation, and you guys have definitively narrowed this down to ferrihydrite. Is this a 100% certainty, or is this we need a Mars sample return to really kind of dig into that, or where are we at with the level of the science here?
I think in order to really characterize the samples in detail, we need those samples back, of course. We're all anxious to get them back. But we have a lot of clues now. We have orbiters flying around the planet and taking pictures of the surface and spectral data, and we have rovers on the surface. So we have a lot of data, and a lot of people have thought hematite was there because the surface was so dry. And hematite is an iron oxide. It's ferric oxide and sort of rusty in that sense, like ferrihydrite, but it doesn't contain any water in the structure. And the big difference with ferrihydrite is that it does contain water in the structure. And so this was sort of, the debate was around how dry is the surface. And we do know from the spectral observations, we can see vibrations due to different molecules in the structure. And there are these vibrations due to water molecules. So we know they're there. And ferrihydrite on Earth is really common as volcanic material alters. So we have the lava and the ash and the glass, and it alters and forms clays and ferrihydrite and opal. And that would be the sort of expected process. And so some people before were saying, oh, but we can't have that on Mars because it's so dry. And so there's been this sort of discussion of, well, maybe it's this really bone dry hematite, or maybe it's something else. So what we did this time, instead of the past studies where I've looked at analogs or looked at mixtures of clays and ferrihydrite or other things, this Adam, the postdoc leading this project, he looked at mixtures of basalt with ferrihydrite. And so he was looking at the spectral properties. So when we look at Mars, one of the best ways to get information is looking at the reflected light. So our eyes, when we look around at our world, we have 3 choices. We have red, green, and blue. But when we're looking at spacecraft data, we have a lot more options. So there might be 10 channels, or there might be 500 channels, depending on the spectrometer. And so for this current study, Adam and I and others did a bunch of experiments looking at the spectral properties of ferrihydrite basalt mixtures And the spectral properties of the ferrihydrite mixtures really match much better than hematite. So we feel pretty confident that we have data now that really proves this hydrated ferric oxide mineral is present in the dust, which is very cool for Mars because it means the surface has a much more water-rich history than sometimes is thought to have happened.
So, sorry, tell us a little bit about ferrihydrite. So it's a hydrated mineral, which means there's water in it. And it forms because of interactions with water. So what does this mean for Mars? What does this tell us about Mars itself?
Well, early on in Mars's history, we know there was a lot of water on the surface because of two reasons. So one, we know there's liquid water because there are huge channels carved, like river valleys and deltas. And if you think about the Grand Canyon in Arizona, it's huge. It's this giant cavernous canyon. Well, on Mars, the largest canyon there is about 10 times larger. So there had to have been a ton of water on the surface carving out these channels. And besides the giant big one, they're everywhere on the surface, these small river valleys and channels that were carved by water. And so there had to have been liquid water at some point. And then we also see minerals that require water, and they require warm water or cold water or salty water or acidic water or basic water. So we know that not only was there water on Mars, that this water was changing its character over time. And because of these differences, Mars was a pretty active, pretty chemically active place, and with all this chemistry going on. And that was a long time ago. So this ancient active Mars was about 3.5 or 4 billion years ago, about the time that life evolved on Earth. So it's kind of interesting to think the time that Mars was so interesting was when life was evolving on Earth. And so more and more evidence, as we collect more and more evidence from spacecraft at Mars, we keep finding more minerals like ferrihydrite and clays and sulfates that required this water and these changing chemical conditions. And that provides more and more evidence that the conditions were available for life to have formed. And we certainly don't know if life formed, and we don't have any evidence of that yet, but we keep getting more and more clues as we look further at Mars. And the interesting thing is then that the planet dried out over time, and it's become this really cold, barren desert. So when you're looking at the surface today, you see this sort of reddish, ochre, dusty material, and there are these windstorms, and it doesn't look very friendly or hospitable. So it's today Mars is very different from the former early Mars at about the time that life was forming on Earth.
So I'm going to welcome in some people, and then I want to get back to talking about Mars. I love Mars. I'm wearing my Mars shirt with all the missions on it, and there's my little ingenuity up here. But let me welcome in some people. So we have people watching from Sweden, Australia, Peru, and the UK, and a friend of mine says they're watching from Olympus Mons, and all he sees is volcano. So, so you have been studying Mars pretty much your whole career. Tell us about how you got into that, how it came about that Mars was the focus of your work. Why Mars? You know, I personally have kind of been in like, I love to study Io, I love volcanoes, and you know, obviously Mars has those too. They're just not active the way Ios are. But how did you get into studying Mars, like specifically?
Back when I was in college and trying to figure out life and what I wanted to do, I was really interested in chemistry, and my degrees are in chemistry and earth science. And I was also very interested in astronomy and focusing on sort of remote sensing of planets became sort of a combination of chemistry, geology, and astronomy. And then when I started looking at research back in the 80s and 90s, there was a lot of work on the moon and on Venus and some of the satellites around Jupiter, and I'm not sure about Saturn then, probably more from Jupiter. But there was little work being done on Mars, and it was kind of a lonely time for us Mars people back then. But I found that Mars was, from a chemistry perspective, it was so much more interesting. And so I kept doing lab experiments to try to understand the limited data we had better. And then finally in 1997, we got Pathfinder data. And then over the years, we've had more and more. And now we have regular rovers sent there. So it's kind of like a kid in the candy shop where we just keep getting more and more data. And
I cannot imagine not having all of this Mars data. Like, for you to say like we weren't really studying Mars, to me is kind of mind-boggling, because you know, you look at my shirt, which starts with Sojourner and Spirit and works its way down, and it's like, but we have so many rovers that we've sent now that it's kind of blows me away that at some point we weren't really studying Mars, that we hadn't cracked this planet really. And so that's really fascinating to know that kind of changed in our lifetime.
Certainly. Well, I think the Viking missions in the 70s were sort of a novel thing, and everybody thought they were going to find life on Mars. And these landers went and did a bunch of experiments, and the kinds of chemistry experiments they ran showed interesting chemistry happening, but didn't show there was any life there. And so I think that kind of dampened the interest for a while. And also science in the 70s is much different from science in the 90s or science now. And so I think as the kinds of instruments that we need to measure to find minerals and identify minerals and characterize minerals, as these instruments were improved over time, they are smaller and faster and cheaper. And so now we can send them on rovers, whereas back in the 70s or 90s, the instruments we needed weren't available. So I think it's a good time in terms of technology development and also our science understanding. So there have been a lot of people studying field analogs and lab analogs, and that all is necessary too to put the whole picture together.
Fantastic. I mean, it's just exciting. It's an exciting time. I think almost I worry a little bit that people are getting kind of disillusioned with Mars. So I am concerned about that. I'm going to welcome in a few more people. Let's see, we have people now watching from New York and Alabama. Please let me know where you're watching from. I love shouting these out. I love seeing where everybody is watching from. So Janice, if you have questions for Janice, please put them in the comments. We are looking for those, and I will get to those in a few minutes. If there are any, please ask questions. So Janice, I think one of the things that you I don't know if you know this, but you did have an influence over my career. When I was doing my internship, my friends a couple of my cohort obviously were doing an internship with you, and you were analyzing CRISM data. And my friend was showing it off, and I thought, I don't understand any of this terminology at all, because I was a physicist and I was doing meteoritics, but I really didn't understand geology or rocks or anything like that. So it actually motivated me to go back and do master's work in geology. So thank you.
That's great to hear. Yeah.
Can you tell us a little bit about CRISM and what it does and what you've used it for? Because that has been a big chunk of your work in the last few years.
That's right. We've been very fortunate to have this orbiter that's called CRISM, and CRISM stands for Compact Reconnaissance Imaging Spectrometer for Mars. And that long name is because it was on the Mars Reconnaissance Orbiter, and they kind of fit that in. And CRISM's kind of a play on prism, because when you're doing this kind of spectroscopy, you're kind of bending the light and looking at different wavelengths. And so as we use the reflected light off of the planet, so basically the sun shines on the surface and then the light is reflected off, and anything in the surface molecules that are excited by this vibration, they absorb that light and take it away. And so we get these dips in the spectrum where light is absorbed, and we're looking for these dips, and that tells us, aha, this one has a clay in it, or this one has a sulfate, based on that vibration. So we're looking at these vibrations of all these different molecules. And very fortunately, the clays that we're seeing on Mars, their vibrations occur in sort of a window between a bunch of atmospheric bands. And so on Earth, we have the atmosphere of Earth and then the atmosphere of the other place when you're looking at a telescope. So they would try to go to the top of Mauna Kea or somewhere where the atmosphere is thin, but still you always have Earth atmosphere and the other atmosphere. And with an orbiter like XRISM orbiting around Mars, we don't have the Earth atmosphere, but we do have the Mars atmosphere. And fortunately, it's much thinner. So the atmosphere on Mars is about 1/100th or 1,000th. It's much smaller than our atmosphere, but still there's carbon dioxide there. And so we have these carbon dioxide molecules vibrating as well. And very fortunately for those of us trying to identify the surface, there are windows between these atmospheric bands. And if these windows align with the vibrational bands of what we care about, the minerals we want to find, then we can identify them. So it's been really interesting and fascinating to identify clays on Mars. And that was, in addition to the ferrihydrite hematite kind of discussion, clays or no clays was a big discussion. A lot of people thought, oh, the planet's so dry, it can't have any clays. But then others of us, like me, were like, well, but all this volcanic material on Mars, on Earth, when volcanic tephra and ash alters, we get clays and ferrihydrite. Those are logical. That's what we should expect. And so it's kind of gratifying that we're finding these now, although I was rather lonely for years with my opinions. So it's kind of nice to see the data catching up with what the rational process should be, and it's also quite nice to see years later that I'm actually right. So that's fun too.
I love that since I was, in my lifetime, that we've gone from Mars is this like, oh wait, there might be life on Mars. Oh no, Mars sucks. Mars is dead. We're not even going to bother with it too. Mars is actually really kind of cool, and there could have been life, and it had water, and we really need to kind of look into these things. So it's amazing how the swings of science have kind of have taken us different places. So for you, what has been kind of like the most interesting, exciting, surprising discovery about Mars that has happened in your research? The ferrihydrite seems like wasn't really all that much of a surprise. You were kind of expecting it. So is there something that sort of made you go, well, did not see that coming?
Well, something recently that's been discovered is a mineral group called phosphates. And some people might have heard of phosphates because sometimes they're on your vitamin pill bottle. But phosphates are necessary for a lot of things. But and they're one of those components that's sort of the essential ingredient for life, and they're necessary for in some of the chemical reactions that we think happen. And so some of the rover analyses at Jezero Crater, they're finding phosphate minerals together with some other sulfur minerals and also organics, and they're finding sort of more organics than were found in other places. And this was presented at a conference recently, and so I'm sure we'll be hearing more about some of these things in the news as time goes on. But there's a place on Mars I've been studying called Mars Vallis, and we see with the clays, we see ferric iron, and then we see some reduced ferrous iron. And this sort of change in ferric to ferrous implies that there's active chemistry. And now they're seeing this at Jezero Crater as well, where they're seeing some transitions from ferric to ferrous. And they're seeing this near some of the organics. And so this doesn't mean there's life. On Earth, we typically see these kinds of reduction or oxidation reduction reactions where there's life. But there are a lot of inorganic ways too. And what it mainly means is where you have unexpected or interesting chemical transitions like this, it means that there was energy in the system that could have been used for synthesis of prebiotic chemicals, prebiotic organics. And so next thing to look for is amino acids or something like that. And we're finding those now in the return samples from Bennu and from Ryugu, and those are asteroids, not Mars, but we are finding some clays and some carbonates and also these phosphates. So I think having phosphates together with amino acids and clays and carbonates, this really tells us that there was an active period, a period of active chemistry for both these asteroids and for Mars. And it'll be exciting to see what the rovers find in the coming weeks and months, and especially when those samples come home, what we're able to determine on Earth. So even though the instruments we send to Mars are better today than they were a decade ago or 2 decades ago, still what we can do on Earth is better. And so once we get those samples back from Mars, we'll really be able to analyze them, and the secrets will be revealed, I guess.
I would like to peel back some of these secrets. Welcome in from North Carolina and Colorado. So we're getting a lot of states in here. I do have some audience questions starting to roll in. Let's see what we have. Zapfan is asking, can we extract water from ferrihydrite?
We probably could. And actually, a colleague of mine in Berlin is looking at resources from minerals and from sulfates and ferrihydrite. Some of these you would have to heat, and ferrihydrite probably, if you have it in the lab, it's sort of like a sponge. It'll absorb extra water and release extra water. But then when it gets to sort of a minimum, it kind of needs that. So I think it would be a little bit harder on Mars to get that last water out because it's pretty dry. So that last little water that it's got, it's going to hang on to that pretty tightly. But there are other minerals on Mars, some phosphates and sulfates and chlorides or perchlorates. And some of these, even at Mars temperatures and low pressures, diurnally, they're going to be releasing water and gaining water. So I think that's a better way for astronauts or, future people trying to get water, like from the Martian movie where he needed water for his potatoes. So if he'd just gotten some of the soil that's rich in chlorine or phosphorus or sulfur, he probably could have collected moisture just from the diurnal changes where some of the water's leaving surface and coming back.
And so by diurnal changes, we're talking, the sun coming up and going down and the temperature going up and going down.
The fall on Mars is a little different than the day on Earth, but it's, I think, 37 minutes longer. So it's not a big change.
It's not a big change. It's pretty comparable.
But on the moon, for example, a day is like a month. So it's a different, the rotation is much different. So the shift from day to night is like 2 weeks or something like that. And it's much longer. So on Mars, this cycle of day to night where things cool off when it's not in the direct line of the sun, that temperature change will allow water to be released from some of the hydrated minerals, and those should be, and of course you could heat some of these up and then you could retain water as well, but that costs energy as well. So it's hard to say if you bring something to Mars with you, an oven to heat up the soil to get the water out. I don't know how much, if you'd be able to get enough energy out of that it was enough to make the oven work. Not sure about that.
So Broken Symmetry is asking, could there be proof of previous fertile soil on Mars hidden beneath all of that red dust? So not necessarily that the soil is fertile now, but could we find evidence that it possibly was fertile millions of years ago?
Yeah, I guess fertile could mean a lot of different things, but definitely, and that's what this listener is asking is a great question, because the surface on Mars is covered with dust and sometimes some rock coatings, and it's sandblasted continually by the winds. But often when we look down a little bit, we see these interesting clays and sulfates and carbon. And many of these are exposed on the surface. But every time like the rovers have a drill or a rat or something to grind off the surface, then we can see much more clearly the minerals that are there. So on the one hand, you think it's astounding that we see anything from orbit, because when you look at the pictures, you just see this sand and dust everywhere, and we're only seeing the surface. But because the wind blows this around a lot, I guess there are a lot of exposed surfaces, and we're averaging 18 meters. So still, if that 18 meters by 18 meters area is mostly the clay or the sulfate, then you can see it from orbit. And so we do see some of these minerals at the surface that tell us that Mars had interesting chemistry. And if you're thinking fertile soil, like fertile with organics or microbes. I don't think that's super likely, but fertile in terms of the clays and ferrihydrite and some of the sulfates, some of these minerals that would support life. So on volcanic islands, this altered volcanic ash is super fertile, and that's a great way to grow plants. And so many of you have been to volcanic islands and you've seen there's been some disaster where everything, like there was a fire or something, or a new lava flow, and everything's just flattened and gone, and there's nothing, and it looks like Mars or Moon. And then over a few years, all of these roots and plants start growing, and it's just so fertile. You could probably grow luscious vegetables out there.
Yeah, I mean, there's vineyards in Spain that are in like these volcanic fields where they've actually like gone into the lava craters and they've got vineyards in there because the ground is so fertile.
It's so fertile,
and,
yeah. I can believe that. They probably make terrific wine.
It's kind of, I mean, it's one of the sort of like two sides of the coin for volcanoes, right? Like they're incredibly dangerous, and you don't want to be caught in the eruption of one. But on the other hand, the soil around them, once it settles, is very, very fertile, and so you want to grow a lot of food there. So people settle on them, and then it's a challenge. I love volcanoes, but they are a little scary.
I don't think I would want to build a home inside a caldera. That would be a little scary, but maybe where the lava flowed or the ash flowed outside, that's probably a little safer.
There is a home in Southern California that is on top of a cinder cone.
Oh, wow.
I want that, but
it'd be interesting to visit, but I don't know if I'd really want to have my stuff there permanently.
So one last audience question here. Jake is asking, how would things change if we had a human team in orbit with these rovers and drones that are on the surface? So, I think this is kind of talking about that possibility of a base on, say, like Phobos. How would that change for your science? What would that impact? And, would that excite you to have people there doing work as well? Would you go to Mars?
Oh, I thought about it a lot earlier. And the problem with going to Mars, it's a long trip. It's about 2 years. In terms of getting there takes a few months, and then you have to wait till the planets kind of align again so you can come back. So it would be a long trip, and it would be fascinating. It would be totally interesting to see. And the reason a lot of people want to send scientists, geologists, people, is for that decision making in real time. So now with the rovers, you have to wait until the communication comes back. And so things are better now. We have more satellites and communication's a little better, but still usually there's like a daily dump of all of the new data, the images and the results from some of the experiments. And then quickly the team has to digest that. Oh, this is what we got. And where are we going to go next? Do we need to analyze that rock again, or can we move on to the next one? So if you had a group of scientists and engineers sitting on Phobos or something, then they'd be in direct communication all the time. So, if you had people, they could be on their own different sleep schedule and in communication, and depending on where the surface was, where the site on Mars was in terms of Phobos, then communication would be much faster. So they might still have gaps depending on that. But if they were to set up a satellite in orbit and they could put it at a geosynchronous site above the landing site, then they'd really be in direct communication all the time.
I just realized I was muted. That would be really helpful. But even with all of the communication satellites that we could put up there, it would be, you still have, to get back to Earth, like there's still a time delay there. You can't help that. There's that, I remember when Curiosity landed and it was the 7 minutes of terror because we had to wait 7 minutes for the information to get back that, what the result actually was. So you're always going to have that time delay. So having people there eliminates that for at least, controlling and making decisions.
Well, the 7 minutes is the time that it takes the light to get back to Earth. Yeah. But then there's the problem of is the relay station above? Are they in contact with the space on the surface? And then when is the relay station in contact with Earth? So you have to have that line of contact in order to send the message. So
yeah, it's complicated.
Yeah.
Space is difficult, people. Space is difficult. So Janice, we're at the kind of the end of our half hour here, and I did want to talk to you really quickly. So you are a member of the International Space Orchestra, is that correct?
That's correct. Yes, quite an eclectic group of scientists and engineers from the SETI Institute and NASA Ames, and we have a fun director, Nellie Ben. She comes out with an idea every year or two, and a space opera on the landing of the moon, or she has a different idea every time, and then we try our best to perform the latest one. And sometimes once we performed at NASA Ames near the wind tunnel, and sometimes we've performed at Davies Hall in San Francisco or other venues. So each time it's something different, which is fun.
And what do you perform? What instrument do you play? An instrument, or you're singing? What's your
I
role
play
here?
clarinet. Yes.
Oh, wow.
Yeah. So that's fun. And my husband plays trombone, and he's also a SETI Institute employee, and so he's also in the space orchestra. And our kids are actually, they're college age now. They're interns. They work on some of my projects sometimes, and they play euphonium. Our son plays euphonium, and our daughter plays flute. And so and I think Nellie's, she had something, I think it was in 2021. It was during the COVID lockdown time. Maybe it was 2020. In any case, we were all playing at home. So she had us playing our regular instruments, but also getting various gadgets from around the house that made noise to record and contribute to the craziness of the orchestra.
And if you do a search for those on our YouTube channel, we do have videos from the International Space Orchestra. Nellie works for SETI, so that's one of the things that we do, and so you can kind of check out those videos of Janice and her colleagues playing music and doing some interesting artistic things with music. So make sure that you go and check that out. Janice, thank you so much for doing this today. It's really fascinating, and I'm always happy for more news about Mars and its minerals, and thank you for inspiring me to kind of learn more about them.
Well, it's great to be here, and always great to talk about Mars. So thank you, Beth.
Thank you, everybody, for watching, for joining us, for asking questions. It's greatly appreciated. As a reminder, the SETI Institute is a 501c3 nonprofit. You can go to our website, seti.org, and click on the Donate or Give Now button if you want to make a contribution. That helps us keep this program running so that we can continue to bring on scientists like Janice and interview them and talk about the amazing science that is going on out there. Next week, I will be back, and I am talking about fossilized microbes in crystals. So again, a little bit more about the possibility of finding fossilized life on Mars, maybe. So it all ties together. I talked about amino acids on Bennu a couple of weeks ago, and now we're talking about ferrihydrites and fossilized microbes. So very exciting times in science. And Janice, next time you've got another paper, would love to have you back to chat about it.
Sounds great.
All right. Thank you, everybody, and have a great rest of the week. And we'll see you next time here on SETI Live.